Hi, everyone. So we're going to start our next webinar. And today we have an exciting topic. So Olu, could you put yourself on mute, please? And we're going to discuss a WebAssembly port of PALISADE, which is a new functionality. And we have a preview version of it released. It was released earlier today. And we also have the team leading this effort and all the core contributors to this project, Olu, Ted, and Mohammed. I mean, they will introduce themselves. I mean, when they do their part of the basically talk today. So, I mean, this is a new exciting feature, and we'll hear more about it. And today's webinar will have two parts, two major talks. The first one will be done by Olu, and it will focus on blockchain applications. And this is the context in which Olu is looking at Palisade. And the second part will describe the actual WebAssembly port. It will provide some examples. It will include some demos, and the speakers there will be Ted and Mohammed. So we'll start with Olu. So Olu, please start and introduce yourself.
Hi, everyone. Thanks for joining us today. I know, depending on what part of the world you're in, maybe afternoon, evening, early morning for some of you. Either way, thanks for making it. And we thought we'd just take some time to talk, as Yuri had mentioned, about some of the applications of Palisade and how they could be applied to not just past technologies, but perhaps also future technologies, and create interesting intersections. So as Yuri had mentioned, my name is Olu. I have been interested in homomorphic encryption for probably not as long as many of you. However, I have been interested in some of the underlying technologies I'm hoping to apply it to for quite some time. So my first foray into blockchain, for example, was in 2014. While I was in college, I and a group of my colleagues had developed a cryptocurrency ourselves, actually. And so that was our introduction to distributed ledger technologies. It was through cryptocurrency. So after we built our own cryptocurrency, we built our own mining rig. It just kind of kept going from there for me, my interest. And in fact, I actually learned how to program in JavaScript and a little bit of C++, not much, through a blockchain project. So my point is that I think we find our interests and develop our skills through the technologies that we are most interested in, and they will lead us to new technologies and new areas of expertise. And I think Palisade is one such area of expertise that will soon find a companion in blockchain technologies. So it's kind of been my thesis for the last year now. And I'm really hoping to show that this thesis is fruitful, right? So if you can look at your screen very briefly, you'll see something like homomorphic encryption for Palisade users. I mean, that's kind of the general topic that we're interested in, but our specific application here is in blockchain and web applications. So we start with just some basic blockchain background for those of you who are unaware as to what blockchain is, what it does. We'll probably introduce some projects and their intersections with full homomorphic encryption. So one such project is DERO. If some Palisade users are on the webinar, you may be familiar with DERO and some of its applications. You may also be familiar with NuCypher and some of its applications. So NuCypher and DERO will be kind of the examples that we're using. So we want to talk about, first, what is blockchain? It's not this. Many of you are used to seeing something like this, perhaps in the media, whatever form of media that may be, on social media, for example, right? People will be pointing out various cryptocurrencies and blockchain-based applications around cryptocurrency, right? So maybe your first foray into this is, oh, this is what cryptocurrency blockchain is. So it's not just Bitcoin or Ethereum or any of these other perhaps speculative digital assets or electronic forms of value. So back of the napkin explanations include, well, it's an existing group of blocks that are sort of chained together where new information is added to the end of the chain and the existing chain can't be deleted. Very straightforward sort of, I think, layman explanation of what this is. we're also interested really in the benefits of this stuff, right? So blockchain is not just money, but it allows a few other things, such as a lack of middlemen, trust-based transfers. Every blockchain relies on something called honest majority. And so the idea is that most people participating in a blockchain-based network are themselves honest and will adhere to the rules that have been set, the cryptographic rules that have been set by the code. So security obviously is provided through the use of cryptographic hashes in blockchains. And this allows us the ability to create contracts, right? The ability to improve things like healthcare. And while this hasn't fully been realized yet, voting is sort of the white whale of blockchain technologies. They're very much interested in the ability to vote or provide voting services in a completely distributed way to ensure that every citizen has a voice in their elective processes, whether at the local level or the federal level, wherever they may be. So just some basic blockchain information, right? For those of you who think, oh, it's cryptocurrency, there's a technology behind this. And then blockchain itself is part of a larger technology called distributed ledger technologies. So very specifically, we can talk about Stuart Haber and Scott Stornetta. In 1991, they described what we currently know as a blockchain, right? So blockchain was a more recent word, but the idea of organizing cryptographic hashes in the form of blocks was something that they had proposed, right? And in a form of, right, chaining these blocks together. Their work was based on, well, their first work really was timestamps, timestamp and cryptographic hash based. So they said, okay, well, look, you can probably put together a few cryptographic hashes of data in an order such that these timestamps can tell each piece of data before it that it comes next, and each data after it that it comes before. And so these things sort of naturally order themselves through a centralized party. So they built this on an earlier concept of David Chaum, and David Chaum had basically written a thesis in 1982 that asked what kind of future would a network of mutually suspicious computers bring about. So you have to remember that this was not quite the advent of the internet, right? So there were still a lot of things that needed to occur in the linking and networking layers before the internet was fully realized at this point. So again, this is 1982. So but the idea of computers being linked together and having to communicate data in vast networks was already something that was being well considered. And it was, I mean, by a few, of course, groups of people, but the idea that each of these computers would trust one another, right? And that they would somehow implicitly just establish some sort of relationship through the rules of whatever network they were following without any sort of enforcement or any kind of ability to provide sort of clear trust mechanisms was cryptographically secured trust mechanisms was sort of absent at the time. That way of thinking was to be developed. So Chaum wrote that in 1982, and then a year later, what we kind of understand as cryptocurrency developed. And so he described basically a way to use digital currencies through this sort of system of linking information in these sort of cryptographically secure networks. So again, Stuart Haber and Stornetta are responsible for blockchain. Chaum is really responsible for digital currencies. It's important to note that both of these things, obviously, while not being the same, are also not the same as electronic cash. So electronic cash is not the same as a digital currency, is not the same as a blockchain. That being said, you can think of a blockchain closer to something like this, right? So it's a system that, as we just discussed, of hashed pieces of information with ordered timestamps that have been arranged by an elected group of people. And this group of people, typically in a centralized environment, if we're talking about the age of Stornetta and Haber, they could be administrators in a network, for example, and in a closed network, would then follow the cryptographic rules to provide this security and ordering and timestamping of information. So Satoshi Nakamoto's big innovation was in 2008, right, was this concept of, well, I can remove the middlemen, right, from this entire endeavor. Right. So instead of having a centralized group of network administrators in a closed network, we can have an unlimited open network And it could be completely decentralized, and we can find a way to have a decentralized sort of set of network admins. So everybody would be the network admin in that sense. Everybody would be responsible for the ordering and security and enforcement of these cryptographic rules. And so that was sort of what gave blockchain life as we understand it, and created this modern concept of a blockchain-based system. Hence the word blockchain being very recent in the literature. So it very simply works kind of like this, right? We have a situation where one hash of information is added to a block. The block has its own hash, indicating this set of information belongs to this hash, and then it connects it through the cryptographic hash of the block to the next block, and so on and so forth. So we want to ask, now that we've understood, right, to some degree, what these concepts are, right, in this brief introduction, right, that there's not electronic money, it's not a cryptocurrency, digital assets are not the full description, blockchain is not the full description. In fact, distributed ledger technologies gets closer at encompassing these types of technologies, even though we're really focusing on a cross-section of distributed ledger technologies called blockchain. To the right, you can see a picture, right, of just how many different types of blockchains exist today. I think the number is well over 5,000, if I'm not mistaken, and each of them provides various functionalities. Some of them copy one another. Others of them have explored really interesting intersections of other technologies and blockchain-based systems, and provided unique value that you cannot find in other systems. But the question that we're asking today is, what happens when we combine the concept on the left, which you can see is a form of homomorphic encryption, just the Wikipedia picture, right, and with what we see on the right? What happens when we combine these two things together? And one such project has done something like this, but I'll pause now for questions just to make sure that we're on the same page.
So just check, there are no questions, but I did mention to everyone that the Q&A feature can be used for any questions at any point. Thank you.
Okay, so I can go on briefly to describe just what we're interested in this intersection. And you'll see that there is a technology, much like something called DERO, that actually explores this thesis, right? What happens when I combine these two concepts on the left and the right? So they're not alone, but it is a relatively recent set of theses in blockchain. And by relatively recent, I mean within the last few years, this has been something that has been seriously considered by these projects. I'm sure many other projects have considered or thought about what could happen if we allowed the combination of fully homomorphic encryption and blockchain, but the actualization and implementation of these concepts, right, is a very recent thing in blockchain. So again, we can talk briefly about something called DERO. It is a project that is claiming to be the first project to combine proof of work blockchain technologies with directed acyclic graphs. So when we talk about proof of work, we can briefly talk about the usage of cryptographic hashes to prove that one has indeed calculated the cryptographic hashes, meaning your ability to actually order these hashes and put them, submit them to the network as a whole, to the other participants on the network, is proof that you've actually run computations to arrive at the correct order. And so you occasionally are rewarded for doing that work in the form of something called a digital currency, specifically a cryptocurrency is sort of the popular term as we've talked about. So that form of digital assets, I apologize, not currency. So the digital asset that we're interested in some cases, usually is related to a particular type of blockchain in the cryptocurrency industry. So DERO is one such, and that proof of work is, that concept of proof of work is something that they've combined with directed acyclic graphs. So we can go very much into the discussion of graph and graph topology, graphs and graphs topology, but that's sort of a different conversation for another day. You may know it, some of you, if you're familiar with this concept in computer science, is called a DAG. And the idea is that blockchains actually work very nicely with directed acyclic graph structures. So you don't necessarily have to keep everything in an ordered line, right? So when you look at some of these blockchain concepts, you think of, oh, it's just a line, right? These blocks just sort of form, one line, right? Like this comes next, then A, then B, then C, then D, et cetera, et cetera. But there are more exotic forms of directing and combining and chaining cryptographic hash-based information. So this distributed ledger that they've created, this project called DERO, has a 60-second average block time, meaning it takes about roughly 60 seconds for each block to form and be added to the chain and create something called immutability, right? An immutability record, meaning this cannot be in any way, shape, or form altered or deleted, right? As we've discussed previously, which is a property of blockchains in general. DERO uses homomorphic encryption and has smart contracts on its native chain without any extra layers or secondary blockchains. So one popular thing that we see in blockchain technology is the usage of sidechains and/or miniature secondary chains, miniature sidechains or secondary chains that are used basically to transfer information that cannot be feasibly transferred on the initial network. And that could be for a variety of reasons. It could include costs. It could include something like lack of trust in the initial network. It could include something like just efficiency gains, for example, right? So not all blockchains are built the same, obviously, because not all software is built the same. There are many ways to solve the same problem. And there are many ways to solve variations on the same problem. And there are many ways to solve combinations of the initial problem with another problem. So you get a panoply, essentially, of different solutions and efficiencies. And DERO is hoping to bring some semblance of order to this entire process by saying, okay, we'll actually rely on the homomorphic encryption for a lot of the security and efficiency gains that we're looking for, and that'll allow us to move forward in that way. So their graph sort of looks like this.
Olu, just may I ask you a question? Just
please, by all means.
A second.
Yeah.
So trying to understand, so the motivation, what is the pain point that you think homomorphic encryption can address, with respect to this like blockchain setup that you just described, just trying to understand why it's important to introduce a technology like homomorphic encryption for this?
That is a solid sort of question, and there are many different reasons. In fact, DERO themselves, offers a few. So let me actually skip forward a bit here, and we can talk about, look, here's some features, for example, right? You can talk about anonymity in the context of blockchain. So with blockchains, the sort of caveat with a lot of the information on these data structures is that it's all visible, it's all public, right? In fact, that's kind of why we like it. There's this immutability, right, aspect. That's the central point. But sometimes you want private information, right? Sometimes you want the ability to be able to compute privately, but honestly, right? So to still follow the rules, but not have anyone else see your information. So privacy, anonymity, these are some aspects of homomorphic encryption. And in addition, sometimes factors outside of the blockchain itself or of the desires of the administrators of the blockchain sort of force that requirement as well. So things like GDPR compliance, HIPAA compliance, there may be all sorts of different compliance factors from different parties outside of the blockchain that require privacy, but still want to access all of these great, amazing features that the blockchain provides. I do see a question, another one here, that asks about the differences, or rather the benefits of homomorphic encryption over zero-knowledge proofs. I would say I don't think homomorphic encryption necessarily can, on the blockchain at least, needs to work without zero-knowledge proofs. In fact, I think they can work together. It is possible to create your own zero-knowledge proofs using homomorphic encryption entirely. And in fact, that's a very interesting direction I myself want to explore. But in my opinion, homomorphic encryption actually extends the functionality of zero-knowledge proofs and allows not just zero-knowledge proofs, but other forms of computation that you would see in multi-party computation to exist in one single system, right? So I don't have to go to string together different forms of software to accomplish the same thing. I can kind of devise my own mathematical primitives and other structures using one set of software. So you get other things like private accounts. So for example, I need to be able to, create a model where I can store my digital assets on a blockchain, and I don't want anybody to be able to see some of that data, right? So I can store whatever it is I'm looking to store privately on the chain while still respecting the rules of the chain. So if we talk more about privacy, we can go on and on and on and on. But there's something called deniability, which is another really interesting feature, meaning someone can't on chain say that, okay, this person did this, this person did this, this person did this, but hey, look, you actually did X, Y, and Z. Well, you can show that actually, no, I didn't do X, Y, and Z, right? Because even if someone had access to my account, they would produce a different cryptographic hash at every time when they're signing for my software. So for example, basically I can, instead of just transacting from my wallet the same way every time, I can change the way I transact from my wallet. So if someone hacks my account, they can actually transact the same way they cannot transact the same way that I do, because I can create a system where there's information in my head that I can actually enter at every transaction to prove that this is, me, right? And if someone hacks into my account and simply, maybe they obtain my keys somehow or whatever it is, uses my account in order to send a transaction, but they forget that there's a sort of a piece of information that they need to append to every single one of these transactions that changes over time or is somehow cryptographically generated that they don't have access to from there. They essentially demonstrate, right, that using fully homomorphic encryption, that they were not me. Right, either that or I had forgotten to do this, to sign this message in a unique way. So it's a difficult concept to wrap your head around when you think of sort of transactions, particularly financial ones, as occurring the same set of ways every single time, as opposed to a different way every single time. But this is one of the benefits that you get from blockchain and homomorphic encryption, being able to have sort of unique transactions every single time that you can verify, basically deny deny the form of transactions that occur differently from that set. Does that make sense? Maybe it's not the best explanation. It's probably better with a demo, but so we can do other things and talk about other aspects of the homomorphic encryption from the DERO chain, including what ring sizes they use, but anonymity groups are chosen in powers of 2. They allow homomorphic assets, which we just discussed. Another really interesting feature when you talk about homomorphic assets on blockchains is smart contracts. So you're already aware of that innovation, but the ability to combine a smart contract with homomorphic encryption to produce, like we talked about, computation that should always execute in the same way because you're relying on honest majority is another really big feature of an application of homomorphic encryption on blockchains. So you can combine, again, fully homomorphic encryption and smart contracts, and suddenly you unleash this sort of whole world of honest private computation. And it could be for assets, it could be for other things, right? That doesn't even require an online scheme. So here's some other things that you can do. You can have very small block sizes. You can have very small transaction sizes with homomorphic encryption. So another thing it does is it reduces the amount of data that is necessary to be sent for every single transaction, because most of the data can be verified using the homomorphic encryption protocols and decryption protocols itself, right? So you actually need very little data then to be able to actually create these cryptographically secure blocks. So here are some ring sizes that DERO has chosen. And you can see that the data is actually not so bad as the ring size increases. Not so bad, I think, in comparison to perhaps other systems that you may be able to find or construct yourself. And I'm going to pause here for questions. Hopefully I've explained sort of the DERO ecosystem and one of the things that you can do with a graph structure, right? Including homomorphic encryption on the blockchain. Okay, I don't see any.
Yeah, no questions at this moment. Please continue.
Perfect. So we're going to talk about one more project, and then we'll call it a wrap on this part. But the project I think is pretty interesting. It's called NuCypher. So NuCypher is itself was a chain that was based on. It wasn't an ERC20 token, right? So there's a blockchain called Ethereum, as you may have heard of, right? Some of you, but for those of you who are unaware, Ethereum is widely considered to be the second most popular blockchain, and that's by market share, if I'm not mistaken, after Bitcoin. And it's responsible for a lot of decentralized financial tools and data transaction based models outside of the sort of blockchains that Bitcoin, Litecoin, and other UTXO based blockchains are based on. So again, it's this idea of proof of stake, not proof of work. And proof of stake implies that we are more interested in demonstrating that the user who has obtained maybe a cryptocurrency or some sort of digital asset, demonstrating that they've done work on the network, is now staking that work in order to gain additional benefits or additional access to future computations at a reduced price. Because remember, the whole system sort of works on a network of administrators working together, right? Completely open, decentralized network of administrators working together. And so they have to perform work, right? In order to actually be able to obtain rewards or this sort of cryptographic security that this entire system affords the blockchain system. So proof of stake, it's a very simplistic explanation of proof of stake, but you can obviously look further into it. Anyway, the point was that NuCypher was essentially based on this concept of proof of stake. And then they've recently switched to a different system than Ethereum. Basically, they're creating their own sort of blockchain that is similar to DERO, actually, that is used particularly for the enhancement of homomorphic encryption based operations, and it allows arbitrary homomorphic encryption based operations. And the whole thing works using TFHE. And so we can, briefly discuss this, but the idea is just that NuCypher is just saying, hey, here's a sort of GPU optimized version, right, of these well understood homomorphic encryption algorithms or variants. So the reason why this is important, the GPU-based implementation, is simply because blockchain itself runs typically on a GPU-based hardware ecosystem, and CPU-based blockchain computations aren't going to get you very far. You definitely want to have powerful GPU or ASIC-based hardware to be able to perform any sort of computation on any blockchain. And so fully homomorphic encryption essentially then would be better served in the blockchain community by the hardware if itself it was sort of used in a sort of parallelizable format, right? So if it was written in a sort of a parallelizable way to be computed on a highly efficient parallelization computation engine, like a GPU, for example. So the benefit of this sort of system that NuCypher has developed, again, this concept of a blockchain-based ecosystem where we can run smart contracts in a homomorphic way, where we can perform homomorphic and private transactions and computations. One of the benefits is, of course, no off-chain coordination, right, to be able to produce complex financial transactions and complex financial systems. There's no interaction necessary at all, really, is what they're claiming. And there's no need for users to even be online. If you think of any blockchain, right, remember, those who are participating in the administration of the blockchain themselves are typically performing these computations. And so they're always online when they're performing these computations, right, as you need to be. So they're using their hardware, their time, their money to perform these computations in the hope of obtaining some sort of digital asset as a reward. Again, that's the cryptocurrency aspect, but that's not necessarily true. But the idea is that they're really contributing toward the security of the overall blockchain by providing their computational power to create the hashes and the blocks, right, of the chain, whether or not there's a digital asset attached to that, even though there usually is. And so again, because they are always online, the rest of us don't need to have that kind of expensive hardware to be able to submit that data. And so we can now perform complicated tasks like fully homomorphic smart contracts while we are offline by just simply submitting our contract and having the miner run it. And so those network administrators, again, called miners, and they perform these functions on our behalf, and we just simply pay them, right, using a digital currency, or if they don't require payment, then we don't pay them at all, because there are some blockchains where you don't pay the miners, aka the administrators, for performing these functions and tasks. So those blockchains seem to be the most interesting for applications of homomorphic encryption to the blockchain in order to continue these sort of complex computations. So thank you very much. That was a sort of brief overview of how blockchain and homomorphic encryption work, in addition to just some projects that make this work in the real world, right? And so we'll start seeing some of these real world applications relatively soon.
Thank you, Olu. Maybe just I have a couple of questions or maybe
Please.
comments, thoughts. Yeah, so this is an interesting example that you just discussed that is based on the TFHE scheme, and so TFHE, I mean TFHE and FHEW, it's essentially the same scheme with different bootstrapping technique, and it's fully available in Palisade. So it's an interesting application where Palisade can be explored. So this is very, very, very interesting. And maybe this was more of a comment, and maybe just I'll add to that. There are also some relatively new and interesting developments related to hardware acceleration, for instance, of FHEW and TFHE in Palisade. So recently, AVX 512 support, so acceleration using AVX has been added, and the Intel Haxel library and Palisade have been integrated together. So this is just another interesting angle, another interesting development.
I actually did not know that. Yeah, that is a pretty big development in the establishment of Palisade, because Palisade provides so much functionality in homomorphic, the homomorphic encryption arena, right? So to bring that functionality into the blockchain arena through hardware optimizations as well, right, is huge. I mean, that's, yeah. So I'm looking. Not many of us in the blockchain community are looking forward to being able to access these tools and functionalities to extend blockchain now into a much more robust, much more powerful system.
Yeah, this is really nice. And maybe now I'll ask probably more of a question. So FHE, there are different essentially flavors and use cases. So one of them is where you use bootstrapping and, for example, Boolean circuit evaluation, similar to what you just described. There are others that may use either just, let's say, additions or single multiplication. So what we typically call as shallow circuits. There are also capabilities such as proxy re-encryption, threshold FHE that are available in Palisade. I mean, do you see all of them being used, or do you see some of them being used? Just trying to understand it, like from the spectrum of FHE capabilities and FHE-based technologies such as proxy encryption, threshold FHE.
I see almost all of them being used. So, for example, it's good that you raised the example of, for example, proxy re-encryption, because NuCypher itself was a proxy re-encryption based platform before they sort of expanded to just general computation, fully homomorphic computation in the blockchain arena. They were initially so they took this thesis of, okay, well, we'll have additional proxies, have everybody serve as a proxy, actually, really, in the construction of whether or not we agree with this, the validity of this transaction. And so they were essentially creating a proxy encryption-based blockchain network in the same way that DERO created a DAG-based network and then leveraged fully homomorphic encryption. And so they just, I mean, they themselves are a good example of an example of proxy re-encryption. Perhaps I would have went about the problem slightly differently than they did, but it was a pretty good example as one of the first examples in the blockchain community. I absolutely see other functionalities being able to be used, including, for example, threshold encryption and decryption. So that is a very large portion of future computations that is currently being done in using multi-party settings. Right. And so we don't have to go too deeply into the difference between multi-party computation and fully homomorphic encryption, but I think the idea is that fully homomorphic encryption absolutely extends multi-party functionality. And like I said, zero knowledge proof functionality as well. Typically, you combine multi-party and zero knowledge proofs to fill in some of these gaps that homomorphic encryption by itself could completely fill. So it's a very interesting set of developments, in my opinion, because I think you will see every single tool that can be used in fully homomorphic encryption find a home in the blockchain network, whatever blockchain network that may end up being. Right? Maybe it hasn't been invented yet.
Yeah, very interesting. Very interesting. So I'm just checking if there are any questions in the Q&A. There are no more questions, so I think we're going to transition to the second part.
So,
sure.
Hi, this is Kurt masking as the contact at Palisade. Actually, one question, Olu, great presentation. I've enjoyed it immensely. I'm actually kind of curious, where do you see as the main computation bottlenecks in your use of the various kind of crypto schemes supported in Palisade? You talk about hardware acceleration, things like that. Maybe you mentioned it, but maybe just like a really clear statement, because we got a lot of engineers on the call that like to do that kind of stuff. So and we're always, solicited of people that want to contribute to the project also, right? Particularly people that are going to do good, right?
Yeah, I mean, I think my colleagues Ted and Ishmael will probably speak a little bit more toward, and in fact, some of the initial limitations that we faced that we've kind of overcome when we were working with Palisade to bring it into the blockchain arena. But I can definitely say things like parallelization that Yuri had talked about, that you guys had already sort of been working on in Palisade, but for other contexts, right? For the web, for example, right? Being able to bring Palisade to like a blockchain-based web environment. I would say definitely preparing Palisade for a multi-threaded sort of future, specifically in its translation to other languages. It would be, I think, a huge help for many blockchain developers. That's thing number one. Thing number two, I would probably mention, you have to be kind of careful about how you used certain sized plain text in Palisade. I mean, because blockchain based systems just kind of shove all the data into one single kind of silo. And so you kind of have to think through this now, right? Like, okay, actually don't do that. I want to be selective and careful about the way I arrange data, as we've seen with DERO, for example, right? You can actually like do the same thing you want to do in the blockchain system with less data if you rely more on the computation side of things, right? So just being careful about how you're using the system, and maybe that includes putting up guardrails, I guess, to answer your question, right? So taking Palisade and saying, okay, now we're going to add, for particular applications downstream, right? Here's some guardrails that you can use to ensure that you always get this sort of systematic standard that you can put in any project, right? So those are some of the things that I think can absolutely be done.
Excellent. Points well made and points well received. Thank you very much.
No problem. Much appreciated. Are there any additional further questions? You're obviously free to reach out to me. I think I may have shared my email through the invite. If I have not, I can absolutely circulate it to anyone who asks privately in the Zoom meeting. But I appreciate it. Thanks for having me here.